Alright, lesson 9.4 begins with just a quick intro to polar arc length, and then we're going to get into the last part of Unit 9, which is the vector definitions and then vector calculus. Okay, so we've been dealing with polar coordinates and graphs and area. Now, what about polar arc length? Well, I hope you remember the arc length formula from, I think, the parametric talk. Remember this thing? dx, dt, don't need to write this down if you don't want to, dy, dt, all squared, dt? Yeah, well, that's the parametric form. I guess we could just replace the t with theta, and then you get d theta, right? d theta, d theta. And then the goal here then is to figure out what dx d theta is and dy d theta, dy d theta is, and then substitute it in. And you can do that because you know x equals to r cos theta. Go ahead and take the derivative dx d theta. Ew, I smell product roll. Do the same thing with y, r sine theta. Find dy d theta. Product rule again. Sub them all back into the equation, and I'll let you do that as an exercise, or you can look in your textbook, but bottom line, you'll get this lovely formula here, where the arc length for any polar curve is actually equal to the square root of r squared plus its derivative, so dr d theta all squared times d theta. So just a quick application here with example number 1. A and b, I know in this case I tell you, are 0 and 2 pi, so the arc length is just equal to the integral from 0 to 2 pi. The function r itself is 2 minus 2 cos theta, all squared. Gotta find its derivative, so what's dr d theta? Well, the derivative of 2 is 0. Derivative of negative 2 cos theta is just positive 2 sine theta. So we're at that now, because that's dr d theta. Don't forget to square that as well, and then your d theta at the end. And once again, you wouldn't do this algebraically. You just go to your calculator, you'd plug it in, and I'll let you try that, but I got the answer being 16. So, just a simple application of the formula. That's how you find arc length. Cool. Vector time. Vectors. You're like, didn't I do this in physics? Yeah, you might have. Okay, so just a quick review if you've done physics before. Well, what is a vector? Well, I'll just give you a quick definition, really. A vector is just, a quantity with both magnitude. Magnitude means like size, right? Not size. Size. S-I-Z-E. And more importantly, direction. Okay? So it indicates motion in either a 2-dimensional or 3-dimensional plane. So what is the actual vector itself, though? It's a directed line segment. So really, it's a line segment that shows you which way you're going, and it also tells you what size it is. So the magnitude of the vector, we use this notation, double absolute value of this. Well, the magnitude is found by taking the x, and we're going to square that with the y squared and take the square root. It's really the idea of the length of the vector. And I'll just quickly show you what I mean by that on this little grid here. This distance here is x. This distance here is y. Then the angle theta is what is here. Then, of course, the magnitude is just the hypotenuse, or the square root of x squared plus y squared. Okay? Now, notice the direction is given by the angle theta. Notice in this case that tangent theta is equal to y over x. So if I actually asked you to find theta, that would be the inverse tangent or arctangent of the ratio y over x. Okay? Arctan y over x. Now, you will encounter equivalent vectors And equivalent vectors are just vectors with the same magnitude. And not only that, they're going in the same direction. So same length, same direction. What's different though then? Well, the key thing is they might not start at the same point. So not start or end at the same point. Okay? And I'll show you an example of that in a second. And then last but not least, what is component form? Well, component form looks like this. We don't use brackets, but we use these kind of like weird sharp brackets, I guess you could say. And really, there's a component form, so x, y, if it's 3 components or 3 dimensions, you get x, y, and z. But notice the x value here is really the difference between the starting and ending x values of the 2 points if it's 2 dimensions, and similarly this would be the difference between the y values. Okay, but just the starting and ending part. Okay, so knowing these definitions, I'd like to just do a few examples and then get you practicing on using and interpreting and understanding these ideas of vector components before in lesson 9.5 we actually do the calculus behind it. So, next page. And over here I'm going to ask you to please actually do some graphing. So notice I've got an initial point of a vector, and by the way these points are back in the xy coordinate plane. So negative 1, 3, that's right here. And its terminal point is 2, 7, so it's over here. So notice it starts from there and it goes all the way there, so I'll draw the arrow like that. And that's how you graph out the vector. So this is vector for part A. Then it says, graph the vector in standard position on the same axis. So the idea is, can you take this vector and shift it so that it's at the standard position, meaning the starting point is on the origin, and you're going to go the same distance to the right. So 1, 2, 3, 3 to the right, and 1, 2, 3, 4 up. So 3 to the right, 4 up. I'll end right here. And notice these two vectors are parallel to each other. Oops, erased too much. Ah, what did I just do there? Give me a sec. Okay, so there are my components. Let me just erase those dashed lines if I could. Good. A and B. Notice, though, they're parallel. So these are actually same magnitude, or the same length, and they're going in the same direction, because they're parallel. So these two are equivalent vectors. Now, how do we find the actual component of the vector? Well, remember, the x component is just the difference between the x values. So 2 minus negative 1, that's just 3. And then the component for the y is just the difference between the y values. That's 7 minus 3, that's 4. And notice that for B vector, the one in red, the component would be the same. Still 3 for the x and 4 for the y. How can you then find the magnitude? Remember, the magnitude is just the square of the x value plus the square of the y value. That's just equal to 5. And if I ask you to find the direction, remember it's arctangent or inverse tangent of 4 over 3. And you use your calculator. So let me bring that back out. Uh-oh, that didn't look good. Let me go back to regular function mode and go arctangent 4 over 3, and that's 0.927. Okay, so that's just the angle and standard position measure to show you the direction that the vector is moving in. Alright, example 3 is yours because it's pretty much the same thing as part E. So go ahead and do the inverse tangent of negative 5 over 3. Oh, negative 1.03. Notice we don't usually give angle measures as negative 1.03. So where is that actually going to be? So think about this. Negative 3 and 5. If I were to start at the origin and go 3 to the left and then 5 up, I've got this as my vector, and this is the angle that I'm talking about for the position. So in essence, that negative 1.3 tells me nothing, but the reference angle is 1.03. The reference angle is this part here, so the actual angle in the standard position will be pi minus that, and then you get 2.01. Now, just to go back a bit, I forgot to mention in example number 2 that these two vectors A and B are equivalent, yes, because they both have the same magnitude and same direction, and they both have the same component form. But B actually has a special name. Because it starts at the origin, we sometimes give this the name position vector. You might see that in a textbook or university courses later on. Just want to let you know that. Okay, back to number 4. If the magnitude of a vector is 6 and its direction theta equals to 2 pi over 3, I'd like you to write the vector in component form. So where's 2 pi over 3? That's probably somewhere like this, where this angle is 2 pi over 3. The magnitude of the length is 6. So the question I have for you is, what is the component form, the x and the y value? Well, by drawing this picture, I hope you can see that this reference angle is pi over 3. And then you can find out the x value by taking cosine of pi over 3. So x equals to 6 times cos pi over 3. In that case, it's, I believe, 3, but because it's in the negative direction, we could just say that this x value is negative 3. And then the y component is this up here, and that would be equal to 6 times cos pi over, oops, did I say cos? I meant sine pi over 3, and I think that's just 3 root 3. Okay? And you're thinking, Mr. Lee, couldn't have you just used these formulas, x equals to kind of r cos theta from like the previous parts? Yeah, you could have. R is 6 cos of 2 pi over 3. You would have gotten the same answer. Y equals to r sine theta. R in this case is your magnitude, which is 6 sine 2 pi over 3. Yes, you would have got the same answer. And so the vector component form for x is negative 3, going 3 to the left, and the y value is 3 root 3 going up. Okay, that's the intro to vectors. Let's get ready to practice.